Good morning and good afternoon, everyone. I am Cynthia Perez, Director of Education at UTC. On behalf of UTC, we welcome and thank you for attending this webinar, Spans to Splices on the transition of fiber optic cable into substations, sponsored by, next slide, AFL. Next slide. Please note that attendees will be muted for the entirety of this webinar. However, you will certainly have an opportunity and are encouraged to ask questions. We ask that you submit your questions through the Q&A function and not the chat function. The chat function will not be monitored for questions. Please note that the Q&A function is intended for webinar-related questions and content only. Please note that after the webinar, you will receive an email from UTC that will contain a link to the webinar evaluation form. This is very important. You must complete the evaluation form to receive a certificate of attendance. You will earn one professional development hour for this webinar. The slides and recording will be available in networks within a week. Next slide. And finally, today's presenter, Jeremiah Tesch, will present the webinar. Type your questions as you think of them, and we will answer as many as we can. Remember, use the Q&A function to submit your questions. And now I'm happy to introduce Jeremiah Tesch. Jeremiah, it's all yours.
Thanks, Cynthia. And hello, everyone. Thanks for your time today. I appreciate it in advance. And I guess we'll jump right into it. So just a personal introduction here. I am an application engineer with AFL. I've been with the company for about 3.5 years. I studied mechanical engineering at Clemson University here in South Carolina. And I have prior experience in automotive, aerospace, and engineering consulting. And then in my free time, I enjoy cycling, hiking, and travel, a lot of outdoors activities. All right, and then on to the topic of the day. So kind of the state of the utility market per se. We're seeing an increased demand for communications volume and technologies. We see a lot of integration of smart technology and, the AI and data centers driving a lot of growth, population growth in general, remote work, FTTX. So you definitely see a increasing demand these days. And as this everything becomes more interconnected. We're blurring the boundaries between different sectors and pools of expertise throughout the utility, as well as telecommunications markets and industries. Just a few examples would be utility versus broadband, power versus communication space on, say, a utility structure, and then transmission line versus distribution, network versus substation. So, like I said, you have kind of traditionally more segmented expertise for these areas, or even just different product lines. But now we're seeing things become more integrated, and it's more beneficial today than ever to have that cross-functional knowledge about different areas, different types of products and solutions, and that sort of thing. So that leads into today's topic, where we'll focus on the network and the substation and how they interconnect. So specifically the transition of fiber optic cable into the substation. And there'd be a few scenarios we'll cover today. Optical ground wire, or OPGW, transitioning from the transmission line into the substation. ADSS is more of a communications cable, non-metallic, so that could transition from the transmission underbuild position, which we'll talk about, into the substation, or even distribution level into the substation. It could also run underground as well. So the ADSS is a pretty versatile solution, but we'll get more into the details on that. So those are just a few scenarios that we'll cover. Supporting topics for this would be just an introduction to optical fiber, the relevant cable types, the transition stages from, say, the distribution or transmission network into the substation, relevant cable attachment accessories, and then splicing and termination solutions. Okay, and just a couple graphics here. So this one on the lower right shows a pretty good image of, kind of a transmission line running into a substation where you have the phase conductors, the optical ground wire up top, and then the ADSS underbuild below the phase conductors. And if you don't know what any of that means, we'll get into it. So, all right, starting off, obviously, we're talking about fiber, so that's an important topic to talk about. So typically for these kinds of cables, we're talking about single mode fiber, where you have essentially a single signal at a time. going through the fiber rather than multiple signals, which is used for more short distance transmission. So single mode fiber typically follows the ITU-T G.652D or G.657A1 standards. Pretty typical, and it's optimized for long distance transmission, such as in your transmission lines. And essentially, to join together multiple strands of fiber, you would use fusion splicing, which we'll talk a little bit about later. This is typically grouped in sets of 12. Say you have a bundle of 48 fibers, you'll group those into sets of 12 so that you can identify which set to splice together first, second and third, etc. And then these also follow a color coding sequence. So rather than, we are not, I guess you could say the fibers are so small, it's not possible to print a sequential numbering system on them. So we use a color coding sequence, a sequence of colors that indicate 1 through 12 in each set of 12 fibers. And then you would use that color coding sequence to identify each bundle of fibers as well. So if you have 4 sets of 12, each set of 12 would be color coded with a string binder, or some manufacturers also use stripes as well. But in some way, you identify sequentially which set of 12 to splice together first. So, and then we also have common fiber counts of 48, 72, 96, etc. And we're up into the thousands now with ribbon fiber technology as well. So, all right, and then you can see there a couple of spools of fiber, of course, blue and orange being the first two in that sequential color coding sequence. These spools can typically hold up to about 50 kilometers or 30 miles of fiber, and then they're used for individual cables depending on the length needed. So, all right, and then the actual cross section of a fiber here for single mode would be the outer coating is 250 microns, and then that's kind of a protective coating, and that's where you would have the coloring integrated into the fiber. And then when you go to splice, that outer light blue layer is actually stripped away, kind of like if you were stripping a actual electrical wire to go ahead and splice that together somehow. So then once you strip away the acrylate coating on the outside, you have your core. So the outer port of the core is just a cladding layer. This is similar material to the actual signal transmission core, but it has a little bit different material makeup, and that's intended to protect the core, the signal transmission core, but also if the signal were to stray out from the center, it has a certain material composition that it will reflect the light back to the center as well. So a couple of functions there. And then, of course, your actual core where the signal travels is only 9 microns in diameter, so quite small. So that's kind of the general cross-section of a single mode fiber. And there's actually a more compact version of this fiber today as well, which we'll get to once we talk about optical ground wire, which is a good segue into the next section here. So now we'll talk about optical ground wire, or OPGW. And if you're not familiar, this originates from the traditional overhead ground wire rather than optical. So this is essentially a metallic cable with no fiber integrated into it. This is the traditional solution to protect phase conductors from lightning strikes and excess fault in the system as well, so that you can keep your electricity running. So traditionally, this was just a metallic cable. And in the 80s, it was conceived that one might incorporate optical fiber for telecommunications into this cable as well. And so thus was born optical ground wire. And so this is a hybrid technology combining both the traditional electrical characteristics of the traditional overhead ground wire with telecommunications capability. And just to kind of provide some illustration of that, on the left here, you have your traditional shield wire or overhead ground wire. And this is still commonly used today. We do see a lot of customers replacing it with optical ground wire, but it is still quite common. And then on the right, you'll see several versions of optical ground wire with different configurations of fiber optic units there. And in the next slide here, we'll talk about the different types in detail. So on the left there, that is the original, the most similar to our original type of OPGW that we made back in the 80s, AFL. We call it Alumicore. You could also say aluminum pipe loose tube. There are different names out there in the industry, but this essentially has plastic buffer tubes in the center, which contain the fibers. And so those are quite flexible and easy to route within a splice enclosure. And again, you'll have those fibers grouped in sets of 12 and then multiples of 12 within each tube a lot of times. So this is the easiest for splice prep. Essentially, you'll remove out all the metallic components, run it into a splice enclosure, and then route those buffer tubes to a splice tray. This is typically larger in diameter than the other two styles because of you have the buffer tubes, the aluminum pipe there, and the wires on the outside. But there's kind of pros and cons to each style. So this is also suitable for high tensions and long spans, which all three of these could be adapted to a number of environments and applications, but some have more strength in certain areas than others. This also has a moderate fiber count capacity. Our designs typically can go up to 144 fibers with the standard 250 micron single mode that we just talked about. All right, and then the second type is called, our name is Centricore. You could also describe it as central aluminum clad stainless steel tube. Doesn't quite roll off the tongue the same way, but this has the smallest potential diameter. It's definitely reduced in size and weight. So you have essentially a stainless steel tube in the center where your fibers are stored. That's encapsulated in a aluminum pipe for corrosion and crush protection, and then it's stranded on the outside with wires. Now, typically for OPGW, we also use two types of wires. So you have aluminum alloy, which is the solid gray there, and then aluminum clad steel with the dark core. So that is essentially coated with aluminum powder to provide corrosion protection as well as some level of conductivity on the surface. And so just to kind of provide that background on the wires there, continuing now with the Centricore or the central stainless steel tube style. This also, like I said, this offers your corrosion resistance and crush protection as well with that aluminum pipe. And then this also has the lowest fiber count potential as you're just using one stainless steel tube. But a lot of people, when they replace the traditional shield wire, maybe they have a 3/8 inch shield wire, so they want to use the smallest potential OPGW to replace it. We often use this style here because it has the smallest potential diameter. All right, and then the third style is stranded. So this is most similar to your traditional conductors, at least in construction, as it's a number of stranded members. So typically we'll strand wires and stainless steel tubes around a central wire there. And so that layer one can hold up to 6 positions typically. And we'll use as many fiber bearing tubes as we need to, and we can fill in the rest of those positions with wires. And then on the outside, we'll have at least one layer of wires. We could add even more if we have an extra high strength application. And as far as the kind of the pros and cons here, so again, similar construction to traditional conductors, not as robust against high corrosion environments, but it's still very robust, and we use it for a variety of environments. We do also offer, or it is possible to use grease on these cables as well if you have extra corrosion risk, high risk corrosion environments such as the tropical regions. I've seen these greased cable used in like Malaysia or areas like that. So that can certainly be done. This is suitable for high tensions and long spans. Typically, if a customer asks me for a solution and they have a very long span, maybe a 4,000-foot river crossing, I would typically use the stranded design because you can add in, more wires and extra strength. You could certainly make solutions with all three of these. You can actually add additional layers of wires to any of them, but we do typically end up using the stranded style for extra long spans. This can also hold the highest potential fiber count. Our designs typically can hold up to 432 with the standard 250 micron fiber. All right, so hopefully that makes sense. I know that was a lot of information. Key properties for OPGW. A lot like conductors, you will have tension ratings, but with since we have fiber, there's one additional tension rating. So typically with conductors, you use the rated breaking strength, which is the cable where the rating at which the cable is actually rated to fail. The maximum rated cable load, in contrast, is for the fiber. So this is typically from 60 to 80% of the rated breaking strength, and this is the maximum tension you should actually design for before the fiber will experience excessive strain and permanent damage. So if you're looking at OPGW, you need to take note of both the MRCL and the RBS in terms of tension ratings. And then you also, of course, have your cable diameter, your fiber count, fault current, which is its capability to run excess current to ground, and then the lightning performance. So these are some of the key properties of OPGW. And a lot of times we have customers come to us asking for a design proposal for a specific application. Some parameters may be more important than others. Maybe they want to focus on fault current and rated breaking strength, and the diameter is not as big of a concern. Something like that is typically a matter of specific focus rather than trying to do everything across the board. So, all right. And then the fault current is, like I mentioned, kind of when you have an excess buildup of current. This goes for the path of least resistance. So OPGW is designed and rated for a certain fault current capability in kiloamps squared per second, or kiloamps squared seconds. And this is generally related to how much conductive metal is in the cable. So you've got your aluminum pipe, your aluminum wires, those definitely contribute to that rating. All right, and then yeah, like I said, more aluminum, better heat dissipation, and so OPGW is typically designed to IEEE 1138, the OPGW standard, and I believe it's tested actually in the lab up to 180 degrees C typically, but different manufacturers may vary their actual rating for this beyond that a little bit. So we typically go up to 210 Celsius in our cables, but it just depends. So, all right, and then so we looked at earlier the traditional single mode fiber cross section. Just wanted to touch on this briefly. So there is also the option in the market of 200 micron fiber. So this has a smaller diameter on the outside, but the same core diameter. So it ends up being splice compatible with the traditional single mode. But this way you're able to fit in more fiber for the same potential space. So essentially a 40% decrease from the traditional 250 micron in size per fiber. And just a couple of scenarios here, and we're about to get back into the substation aspect of things. Just wanted to give more of a kind of a background here. So the use cases for the 200 micron, so you could increase fiber count for the same cable structure, keep your same diameter. So on the bottom left here, you start with a 96 fiber, essentially half-inch diameter cable here, and then you could keep the same cable structure but increase your diameter or your fiber count to 144. And the second use case could be to actually decrease your cable size and weight while keeping the same fiber count. So just wanted to briefly mention that as another thing that's kind of becoming more popular in the market. All right, and just kind of to touch back on how OPGW relates to the substation. Of course, like I mentioned, this is providing lightning protection, the path to ground for fault current, and also your telecommunications. So primarily in the utility or the transmission line space, this will be providing telecommunications for just asset monitoring and control. So monitoring your substation and other assets along the power grid. But we do see some utility companies leasing out fiber to third parties, and but a lot of them have restrictions on the ability to make profits and things like that. So definitely understand that. So, but those are some of the use cases. But primarily, the transmission or the optical ground wire is used for just asset monitoring and control. So, and then of course, substations are a highly electrified environment. So the optical ground wire actually has to use a transition cable to enter the substation, and this has to be dielectric, jacketed, and underground typically, but definitely the dielectric. So you do have your phase conductors running straight into the substation, but these communication cables don't necessarily need that conductive capability because they're just there for the communications at this phase. So we would typically use a dielectric cable of some sort. All right, and then on to the other styles of cable relevant to today's discussion. So we did mention ADSS briefly. This is an acronym as well for all dielectric self-supporting. This is a jacketed fiber optic cable and dielectric, so it has no metallic or conductive components. It's optimized for aerial distribution level networks and transmission line underbuilds. So essentially installing the ADSS below the phase conductors. So it's essentially you're sandwiching in the phase conductors between the OPGW above and the ADSS below. You can see in the schematic on the bottom right, I've highlighted the ADSS in red. So this is, excuse me, this is what we call an underbuild scenario for the ADSS. And this is rated for a certain amount of electrical exposure. Obviously, the conductors implement or introduce a certain level of electromagnetic field. So we definitely monitor that when we're installing ADSS on the transmission line. And there are additional measures we can use. I believe I may have a slide on that later on that electrical exposure. But yeah, so ADSS in general, it's a very versatile solution. It can be run directly into the substation since it's already dielectric. It can actually be used as a transition cable as well, running underground or aerially. So very versatile. And typically fiber counts can go up to around 432 for this solution. That's definitely for our ADSS, but it kind of varies throughout the industry. And just to kind of highlight a few of the construction elements here, typically ADSS is stranded around a central strength member or FRP rod. This is a fiberglass rod, and then it's fairly flexible, but this kind of just provides a stranding member, kind of like on the stranded OPGW. And so we wrap or strand fiber optic buffer tubes around this to keep the fibers contained. And so this is generally a certain number of positions to maintain a circular profile there. And then those buffer tubes are wrapped in a few protective elements. And you could have one or two jackets, and you also have aramid yarn providing a bit of tensile strength for different applications. So yeah, essentially you have the central strength member, buffer tubes holding your fiber, several layers of protective materials, and then your jackets and your aramid yarn as well. So, of course, the ripcords as well. All right, and then yeah, just once again, so this is typically holding single mode fiber, but there are other types of fibers that are sometimes used. Your multi-mode can send multiple signals at the same time in different modes of the light wave. So there are other options here, but still primarily single mode. All right, and then as far as the design approach for ADSS, this is actually a highly engineered solution. So this is customizable to different loading conditions. You have your central strength member, as I mentioned. This provides like kind of a base level strength, tensile strength to the cable, but the aramid yarn, we can kind of fine tune the amount of yarn in the cable to adjust it for different strength needs and loading conditions. So say a 500-foot span, 500 feet between two structures versus a 2,000-foot span. Obviously, you'll need a lot of significantly different strength ratings for those two scenarios. So we can vary the amount of yarn in the aramid yarn in the cable to help with that. And then, of course, you have your multiple jacket options as well as tracking resistant jacket for the highly charged environments on the transmission lines. And also with these buffer tubes and cables, we are incorporating a bit of extra fiber length, which has a little bit of a wave. You can see here in the EFL in tube. So there's a little bit of a wave pattern of the fiber within these buffer tubes. And this, and then there's also the tube helix of being stranded around that central strength member. So a couple of elements of extra fiber length incorporated to these cables so that the cable can stretch without actually stretching the fiber. So we have a little bit of cushion there in terms of flexibility, of actual physical flexibility. All right, and then as far as the inputs we use for ADSS design, so you have maximum span length, as I mentioned, pole-to-pole distance, environmental loading. Typically for the US, we use the NESC zones, so light, medium, and heavy, and those incorporate ice, wind, and a certain level of safety factor as well. And then you also have a preferred installation sag, typically 1% to 1.5%, any ground clearance requirements, line voltages, and that sort of thing. and just kind of illustrate the spans here and the sag. So this is a 500-foot span scenario. So typically your installation sag will be 1 to 1.5%. So at a base level, you have that certain amount of sag. So for the 500 foot and say a 1% installation sag, it would sag 5 feet from the horizontal line. So, and then if there's any additional weather loading, environmental loading, it could sag even further down. Maybe some ice here would pull it straight down, or a crosswind would push it sideways. All right, and then as I mentioned, there's some electrical considerations if you're on a higher voltage transmission line. So you have some risk to the cable from dry band arcing or tracking, and then corona. So we have solutions for that, and we actually, AFL performs an analysis for customers, and there are different, I'm sure other manufacturers have different ways of handling this as well. But we kind of perform an analysis on the structure based on relative position, voltage, and things like that. And we can offer solutions such as just simply reducing the height of the ADSS, which obviously there are sometimes limitations. You can only go down so far, but that's often an easy way to reduce the risk to the cable. And then tracking resistant jacket material provides a little bit more protection against that tracking effect. And then of course, corona rings. All right, and then onto the additional cables here. So we have typically for your transition cable, you'd use a duct cable that can go underground. So you have your loose tube. Traditional loose tube is just a standard density dielectric cable optimized for duct installations. This is a lot like the ADSS, but without the aramid yarn, so the additional strength material that allows it to be self-supporting between structures. So this can be lashed aerially in the distribution space or installed in duct. Typical fiber counts could be around 216 or higher. Our current solution is at 216 at the maximum, but I'm sure it varies throughout the industry as well. And we also have the option in the market of microduct. So this is a smaller diameter loose tube cable, very similar again to the ADSS and the loose tube. So this, but it's even more compact. So it doesn't have the aramid yarn, and it has a thinner jacket as well. So it's even more compact and optimized for microducts. So this can also be lashed or installed in duct, and has a typical fiber count range up to 432. And you can see here we have highlighted green. We are running the transition cable from the splice enclosure on the structure into the substation, and we'll get more into that as well. All right, on to the transition to the substation. So just kind of an overview here of the materials required or helpful for this process. And I'm going to kind of break this out into phases. So the first phase of the transition is securing your cable to the end structure. So you can see on the bottom left here, 2 green circles highlighting on the top there, your optical ground wire being secured to the final structure. And then the lower green circle shows the ADSS in the underbuild position. So this is typically accomplished with some sort of dead end. And these generally clamp down or compress the cable in some fashion. But since it's fiber optic cable, we have to make sure we have limited crush, because excessive crush would cause damage to the fibers. So this is specific hardware for fiber optic cable, but it still essentially provides some level of compression on the cable to secure it in place. So for optical ground wire, there are multiple styles. AFL offers a unique bolted style. The formed wire, though, is pretty common throughout the industry. So you have essentially um, flexible wire wraps that have a bit of a friction increasing coating that help grip the cable a little bit more. And so this essentially just wraps the cable with wires that hold on to it. So there are different styles, but these are just a couple of examples for optical ground wire. We also use ADSS formed wire dead ends. So these are very similar in concept to the optical ground wire formed wire dead ends. AFL specifically offers 3 tension levels for these as well. So different tension levels for different strength cables. We also offer a wedge dead end that also just kind of provides 2 clamping wedges, I suppose. But there are a couple different styles throughout the industry. And then just an example here, of course, this is not a endpoint of the line, but this is a distribution level double dead end scenario. So you have two sets of ADSS being having secured, I guess, to this structure here, and it looks like one of those sets is running down the structure as well. Okay, and then the second phase would be to run down the structure to either the splice enclosure, or the ADSS could pass straight through the structure to the substation. All right, and this is accomplished using downlead clamps. So these essentially are secured to the structure somehow, whether it's banded, clamped, or even a lag bolt for perhaps like wooden structures. And these clamp down to the cable as well, and run it down the structure so that it can't be blown around by the wind and things like that. So you typically place these every few feet on the structure. I have a couple examples here. So on the left here is a a distribution structure where you have, that's kind of the photo we probably just saw, but this shows as well the downlead clamps running the cable securely down the structure. Sorry about that. And then on the right, we have a transmission structure with a number of clamps, maybe not spaced out equally, but they are running the cable down the structure every 2 or 3 feet or so, something like that. So those are typical examples. And then once you've run the cable down the structure, you would also use a splice enclosure depending on your application and scenario. So in the case of this ADSS running through the structure, you probably wouldn't need to splice at this stage, but for the OPGW, you would definitely need to splice to a transition cable. So as far as splice enclosures, there's a variety of options in the industry. Just a few examples that we offer here. So you have a metallic structure mounted solution that's bullet resistant by default, and this can hold up to 4 cables and I believe 144 splices. We also have a non-metallic structure or structure mounted solution here as well, and then a more modular multi-use solution as well that can be adapted to multiple scenarios. So these are just a few examples that we offer, but every manufacturer offers their own styles here. And so, but the main function is to provide a sealed enclosure where the splices will be stored for long term, but should be easily accessible in the future for repairs and additions as well. But yeah, so some common features here would be the ballistic resistance in case it's in a rural area and there's some risk of that sort of thing. Modular construction. Of course, there's mounting options of structure mounted, strand mounted, and hand hole. Typically for this application of the relating to the substation, we would be focusing on the structure mounted. And then there's often a variety of enclosure accessories, connector kits to provide sealed enclosure access for the cables. Splice trays, that's where you would store your splices and route the fibers. Bifurcation kits provide routing of fiber into the enclosures in the case of optical ground wire with stainless steel tubes, because the stainless steel tubes are not flexible enough to be routed within the enclosure. And then splice protection sleeves are pretty common. You definitely need those for each splice. So it's essentially a heat shrink tube with a stiffening rod to protect that splice from bending. And then bullet guards, of course, for your ballistic resistant needs. And then you could also use, it's often recommended to use a slack storage solution. So on the structure mounted options, you would use some sort of bracket that provides both cable storage as well as enclosure mounting. And so that would be one solution definitely recommended for this scenario. And we typically recommend storing about, I've seen maybe 200 feet or so, somewhere around there, as for slack storage. That way you can actually take the structure or the enclosure down to the ground to your splice trailer and have the extra cable length to be able to splice it at the beginning, but also some extra to do repairs in the future. Now, this is not as relevant to this scenario today, but I also wanted to mention the strand-mounted storage solution. This is typically used for more of the dielectric communication cables, but you essentially loop back and forth the cable, and then it wraps around this snowshoe on the end, which is what it's typically called in the field. And the snowshoe provides, of course, the loop, but also protects the minimum bend radius of the cable to protect the fiber. All right, so now we've spliced our OPGW to the transition cable, or perhaps we've passed the ADSS through the transmission structure. So now either the transition cable would run underground to the splice hut, or the ADSS could run aerially from the last transmission structure to the splice hut without going underground. So a couple of routes there. And then once you get into the substation, so you have your ADSS entering aerially or your underground duct entry from the bottom there. Excuse me. Um, so then you'll route your cable to the termination points via the raceway. And then you have rack mounted termination, which is the preferred primary approach, and then wall mounted solutions for kind of your second option if you run out of rack space. All right, and so on to the rack mounted solutions. I just wanted to show kind of the legacy or previous generation approach to this. So typically in the previous generation, you had your splicing and termination split into separate stages on the rack. So this here on the top right is a single unit, but you have your splicing designated for the lower section and the termination in the upper section. And I believe this is a 144 fiber unit, so that took up about 10 rack units, which I believe it provides a decent amount of space for the technician to do the splicing and termination, but by today's standards, it does take up a lot of space. So that brings us to today's generation, which is a more modular, compact approach. You essentially are doing your splicing and termination within these splice cassettes, and those can be installed into the main rack-mounted panel there. So this example panel would hold 144 splices and terminations in a 2-rack unit panel, in contrast to the 144 10-rack unit in the previous slide there. And you could also hold 288 in the 4-rack unit panel. So quite a reduction in size there with this new generation. And then the cassettes are where you would perform your splicing and termination. And so essentially each buffer tube goes to its own splice cassette, and rather than having them all kind of go splice together in the lower section and then go up to the termination area. So it's a very modular approach, much more compact, and you can remove your splice cassettes for the splicing and termination. You can also start out with kind of an empty panel essentially, and then build into it as your network grows. And then, as I mentioned, so your rack-mounted options are the first option you would use, the preferred option, but you can also use wall-mount enclosures. These typically are also modular and use the splice cassettes and can essentially hold up to the same amount of splices as well. You also have your, to just kind of focus on the patch and splice modules. Again, so each buffer tube will go to its own splice module, typically up to 12 or 24 interconnections there, different connector styles available. And yeah, so an example scenario would be to outfit a 4-rack unit rack mount panel with up to 288 connections using these modules. And then for high density needs, of course, this is not relevant to most substations today, but just wanted to make mention of this. So there are high density solutions these days for more the AI data center hyperscale applications. And these offer even further compact, space management here. So for a one rack unit panel, you could hold up to 144 with your traditional LC connectors. And then there's even the MPO option of even higher capacity. So these are much more compact, and you can see even here the cassette is much more slim, and you have your MPO connector as well. So of course this is AFL's example, but I'm sure there are other solutions like this in the industry as well. All right, and then on to splicing, testing, and inspection. So obviously with fiber, the splices are a key element of the whole network. So you want to make sure you have quality splices to ensure low signal loss and long-term connectivity. So essentially each event in the fiber length is a loss, it causes loss. So you have, say you have a bend in the fiber, you could have a splice point, you could have a connector. Each of these events causes some typically level of signal loss in the fiber. So you want to minimize those connections and events. And so that's ensured by making sure your connector surfaces are clean, your fiber is clean before splicing, you have a good, nice cleave when you essentially cut the fiber for splicing. You want to have a nice perpendicular end face, and then obviously your equipment should be of good quality and be well maintained and that sort of thing. The splice units we have these days are very high tech. They can actually detect the perpendicularity of the end faces and line them up automatically and that sort of thing. So they're very capable, but there are a few things you have to do on the technician side to make sure your splices are of high quality. So obviously these cables are rated for, 30, 40 years. You want those splices to last just as long. And when a company is planning out its optical network, you're planning for a certain loss budget. So you assume you'll have a certain amount of signal loss based on the amount of splices you have up front. But then you also have to account for future repairs. Maybe you have a few severe storms over the years and you have to replace some cable. That adds in multiple splice points where you're introducing additional splice loss or signal loss, and so you want to account for that potential loss in the future as well through the life cycle of the cable. All right, and then you also have test equipment to monitor the signal throughout the fiber. So let's say you have, even just without the cable, a 20,000 foot spool of fiber by itself. You could send a signal throughout that fiber and make sure that it's continuous. There are no breaks or anything like that, and you can actually measure the length of the fiber as well. So there's an array of test equipment and inspection equipment as well you can use to make sure that you're having quality splices, that your cable is sending signals with no problems. There's no events, no breaks, anything like that. It's actually recommended when you receive a cable from a manufacturer to do that testing. Make sure it's testing as it did at the plant. There was no damage during shipping and that sort of thing, and also do that again before installation to make sure that you have those data points between manufacturing, shipping, storage, warehouse handling, that sort of thing. You have those data points that the cable was in good condition at certain points before installation. And so if anything happens during installation, you know the last point at which it was in good condition. All right. And then, of course, you have cleaning solutions. Once again, you want to make sure your connector end faces are clean. So maybe a little bit small in the screen here, but your fiber inspection system image there, the screen is actually showing the end face of a connector, with that dark circle being the actual fiber within the connector. So that is used to inspect your connector end faces and make sure there's no oils or dirt or anything like that. You also have the option of field installable connectors. So these are used typically just for additions, repairs, and changes. So these are not intended as a primary connection solution, but if you need to do quick field repairs, these are certainly available. So you have a couple types here. So splice connectors, if you have a fusion splicer or a splice team available, you could do that. And that's probably going to provide a little bit better of a connection. But you also have mechanical connectors if there's no splicer available. And so there's a couple of types there. And of course, you have multiple fiber diameters that these are compatible with, multiple connector types available. And I know AFL offers toolkits for these. I'm sure other manufacturers do as well. All right, so then let's just kind of recap everything. So we talked about the fiber transition, aerial or underground, must be using a dielectric cable either way. We talked about the cable accessories required to secure the cable to the structures. We talked about splice enclosures, which provide a sealed housing for the splice points, and then splice cassettes, which provide a kind of a modular splicing and termination housing for each buffer tube. Modular panels, either for housing the cassettes, either rack mount or wall mount. Of course, the splicing, you have an array of test and inspection equipment for the splicing and connections. So, and then I think also the different types of cables that we talked about as well. So hopefully this was a informative and educational presentation that you guys can take a few things away from. But again, thank you for your time and really appreciate it.
Okay, we have questions come in.
Sure.
Is there a core size difference between G652 and G657, or both are 9 micrometers?
They are the same size. Yes, good question. So those are very similar. They just have a few slightly different properties.
Okay. Is there an overall limit to how many strands of fiber can be on a transmission line or transition line? Can
Transmission line.
four okay,
Yeah.
can 432 strands of OPGW coexist with 432 strands of ADSS? If that's feasible, have you seen installations like this?
Yeah, great question. So it is definitely possible to have high fiber counts on OPGW like the 432. It's not as common. Typically, like I said, most utility companies are just using this for asset monitoring and control rather than leasing out a number of fibers to third parties for, say, internet or service or something like that. So typically, we're staying around 48 fibers to 96, 144, maybe 288. We definitely have the capacity for more, but the most common that I see is up to 288, maybe 144. And then regarding the second aspect of that, whether you can have 432 OPGW and a 432 ADSS, those are definitely splice compatible. You can maybe you have a section where the OPGW can't go above the transmission line for a certain span because there's another transmission line going overhead in a different direction. You could definitely run your OPGW down the structure, splice to an ADSS, go to the next structure, and go back to OPGW. So they're definitely splice compatible. It's mainly just about the fiber that's in each cable.
Thank you. Does the NEC 50 rule for terminating outdoor cable to a transition cable still apply to utility substations when using loose tube as a DSS fiber? Can you just run them directly to a cassette-based patch panel without a transition cable?
Okay, so that's about, I believe the ADSS, you can't run it within a premise a certain distance. That'd be what you're relating to. But to my knowledge, I believe in this scenario, the ADSS can go straight into the panel, and you break out those the buffer tubes to the cassettes, as I mentioned. So this scenario would be something like that.
From the transition OPGW to the substation, the spliced closure need to be grounded.
We typically, yeah. So I'd recommend grounding any metallic items such as the OPGW. Typically, the OPGW, I believe, is grounded above the splice enclosure, so you may not have to specifically ground the splice enclosure, but it's definitely a good practice to ground all your cables and all the metallic elements as well.
Do you have any design tips for anti-ballistic measures other than using the SBO1 pucks? We find people often shoot our slack loops and we have to run an entire new span.
Yeah, so definitely the enclosures are a good measure, but there's not a lot you can do when it comes to shooting the cable itself. I have seen pictures of ballistic damage to OPGW, and I believe it, would break a few wires potentially depending on the caliber of the shot. Of course, jacketed cables. Sometimes I've seen ballistic resistant solutions for that. Um, but yeah, essentially, it's pretty hard to. I mean, there's armored cable as well, but you don't typically install that aerially. That's intended for direct bury underground. So yeah, I mean, limited solutions for cable at this point. Um, that's a tough one to protect against along a full length of the network. So, but good question.
As utilities increase bandwidth demands and edge connectivity, how do you see fiber transition architectures evolving over the next 5 to 10 years?
Yeah, good question. I think probably continue increasing fiber counts. We'll probably see more use of ribbon fiber, which I didn't talk about today, but essentially you can splice 12 fibers at a time, and they're all kind of interconnected together. So that's definitely one thing we're seeing a lot for the data centers and AI, high demand for the ribbon fiber. So I would expect to see more use of ribbon fiber and increase in fiber counts at least.
When running OPGW or ADSS on transmission lines, how much help does AFL actually provide on the design side of projects?
Yeah, so AFL actually does. We design the cables, but we do not provide design services for the projects. So we'd recommend going with a EPC firm or maybe internal resources, depending on what's your structure there. But we provide the cable and the accessories and things like that. We do not currently have a group to do actual project design.
How important is cross-functional collaboration between telecom, protection and control, and substation engineering teams in accelerating grid modernization projects?
Yeah, I would say very important. Obviously, they all have adjacent functions and interconnections, so it's definitely helpful to understand each other's roles and the solutions being applied to be as successful as possible.
Okay, let me see. Hold on. What testing and validation procedures should utilities perform after fiber installation to ensure long-term network performance?
So as I mentioned, definitely want to test the fiber and inspect the cable visually before installation to make sure that it was in good condition beforehand. That way, if anything happens during installation, then you know the last data point at which it was good. After installation, you want to do that fiber testing again. So essentially, shoot a signal down each fiber and see if you see any events on the OTDR, optical time domain reflectometer. So that's what we typically use to test fibers and make sure that they are sending signals properly. So after that installation, I'd say you could do a visual inspection perhaps as you install it to make sure everything looks good along the line. You know, a lot of people install with a helicopter these days, so they would probably do a run down the line. You'd also be doing your installing your attachment equipment, your dead ends and suspensions, that sort of thing. So definitely, you know, take a visual, pay attention as you visually as you install the cable, but definitely also test the fibers after installation as well with the OTDR.
Can you discuss the challenges of multi-mode and single-mode fiber OPGW and how to handle that conversion?
Do you mean as far as splicing them together or just the differences?
She didn't indicate, so
No worries. Yeah, so they are typically, I would say they're probably not splice compatible. There are some different versions of single mode that you can splice together, but I would not consider single mode and multi-mode splice compatible. Um, and like I said, the single mode is your typical option for OPGW, but multi-mode we do see occasionally. The issue with multi-mode in optical round wire is it's just very short distance transmission, so you can't really use it in a long distance application like OPGW is typically used for, but we do see it occasionally.
does AFL every off does AFL offer any training courses for dealing with ADSS or OPGW?
Yes, we actually offer, so we have dedicated application engineers for different product types. So I focus on OPGW and ADSS for a certain region in the US and the broader market. But we have a team of engineers that are happy to provide trainings as far as just introduction to the product line, the solutions, and excuse me, the installation practices, hands-on demonstrations for splice preparation, installation, hardware accessories, that sort of thing. So definitely have a lot of resources for that. Um, and we have a lot of online resources on our website as well. So yeah, if you guys are interested in any of those things, we're happy to support and feel free to reach out.
Okay, that's all I have so far.
Good question, guys. Thank you.
Well, thank you so much. Just another reminder that the presentation slides and recording will be available in networks within a week. Once again, I want to thank our presenter, Jeremiah, for a very informative presentation. And thank you all for attending. Have a great day, everyone. Thanks again,
Thanks, guys.
Jeremiah.
Happy to help.
Bye-bye.
Have a great day.
You too. Bye-bye.